The topic of our today's webinar is vertical SDS page, the basic knowledge. Why is that important? It is important because it answers a lot of questions that may arise during SDS page. If you know the basic knowledge, then yeah, most questions, most problems are explainable. And so this is our topics in this webinar. First, we will talk about the electrophoretic mobility, sample preparation, then the big difference between zone electrophoresis and SDS page, and we talk about isotachophoresis and the Lamley system itself. This leads to a troubleshoot section and the Q&A at the end. Again, everything that I explain, all the recipes and so on, are found on our information center, electrophoresis SDS page, and then you find the recipes there. So no need to note stuff down. Simply listen and watch the webinar. You can watch it again on YouTube then. So first of all, I'm sorry, we have to talk about much physics today. A little bit of chemistry, but mainly physics. So I try to explain this in easy words and understandable so that everybody of you can follow along. First of all, what is electrophoresis? It is a simple movement of some kind of a charged particle in an electric field. This is schematically a tank with some liquid in it and a cathode and an anode. And why do particles move to the electrodes? In physics, this is the particle velocity. And this particle velocity is, of course, influenced by the electric field strength. But not only that, it is also the product of the electric field strength with the electrophoretic mobility of a particle. What does that mean? If we take a look on the electrical field strength, then this is mainly produced by the parameters you programmed on your power supply, of course. So it's the volts and the amperes, and the product of both is the watts. But that's not the only truth. You also have your buffer. Your particle is inside, and this buffer may have a special pH, may have a different ionic strength, the conductivity, the viscosity, everything of this liquid you are working with is important for the electric field strength. But not only that, it's also the temperature, because the Brown molecular motion is depending on the temperature. The higher the temperature, the faster molecules or particles move itself. The electrophoretic mobility is a combination of the charge of this particle, and this charge can be influenced by the pK itself, so the loading, the minus, the pluses, but also don't forget you can have hydrate or ion shells around it that may be a positive or negative effect to the charge. And it's the size. So depending on what mass it has, what volume it has, so mass and volume is not the same, and the structure itself. So when we do electrophoresis, the electric field strength is identical for particles because let's talk clear, it's the proteins, but it could also be the DNA, in electrophoresis. So the proteins are in the same buffer with the same conductivity. So we just simply presume that it is identical for all the particles in our electrophoresis setup. That is a good thing. But the electrophoretic mobility, here we have huge differences. So when we talk about the proteins, we want to separate according to the molecular weight in an SDS PAGE gel. So we want to measure the mass. But what about the charge, the volume, and the structure? This is from protein to the next protein, completely different. So we need to do a sample preparation to get rid of the differences of the charge, the volume, and the structure, but leaving the mass as a variant. Then we can do electrophoresis and see differences between the particles. So talking about the volume and the structure, I mean, the volume is three-dimensional. And most of you perhaps know that you can have various volumes and structures in proteins. So here are the three most common ones, I would say. So you have some kind of a Y-shape antibodies, for example. You can have column-like appearance, like in membrane proteins. And the biggest part, I would say, is some kind globular structure you find. So these structures are formed by different bonds that you have. So you have this amino acid chain, and between the windings and else you have such bonds. Four of them. First of all, and perhaps known by everybody, is the disulfide bridge. It is a sulfide covalent binding between two of them, and you have three that are not covalent binding. So you have hydrophobic bonds, you have hydrogen bonds, and of course ionic bonds. And depending on the build-up of the amino acid chain, those protein bonds will hold the complete structure and volume of your antibody together. And depending on the work that has the protein to do in the organism, this is also built up by our cells to have volume and structure according to their need, especially the membrane proteins as transporter of ions inside and outside of the cell itself. So how do we get rid of those bonds and thus the structure? For the disulfide bridge, we need to cleave this with a reducing agent, and the most prominent one is the mercaptoethanol. All the other threes, the hydrophobic and hydrogenic and ionic bonds, are quite simply to remove with a simple soap. So this soap is, as in the name of SDS PAGE, of course, the SDS, the sodium dodecyl sulfate. You see it in green here. It's a 12 carbon long hydrophobic trail with a sulfur minus loaded head, you can say. The disulfide bridge is a covalent binding, and one may say this is quite hard to remove. But luckily, there is a rule in chemistry that is the entropy, or the raising of the energy of the system. The better the energy in a system, in a chemical system is, the easier it will be that a reaction starts or is possible. And here we have the so-called proton exchange. It's called like that. So you see, you have two mercaptoethanols that when you just face them together might have the same appearance as those two sulfides here. And by cracking this and receiving two half-long pieces of your protein or your bond, the energy is much higher than a long one and two small particles. So it's just simply raising entropy and raising the energy. So you just need a really minor reaction with 95 degrees for 5 minutes, and this is enough to let these proteins exchange the place here with the sulfides, and then you have here the disulfide bridge, but on your protein the cleavage is done and the bond is broken. Ibel et al. In the European Journal of Biochemistry checked what happens when you do this. So you have this mercaptoethanol and the SDS, and you cook it for 5 minutes. Then you have approximately that appearance. So you see that the sulfides are hydrogenated, and this SDS is aligning, you can say, along the amino acid chain, and on areas where you have a plus loading somehow, a plus charge, you have these sulfate heads or gathered around. So it seems like a necklace, thus they told it would look like a necklace structure. Just some side facts of the SDS. So one could use multiple hundreds of soaps if you like. So there are many on the market, but SDS is still the way to go because one found out that it solubilizes almost all the proteins. Due to the minus loading, they all migrate in one direction then because the plus loading is blocked. Thus, the bands are also easy to fix because it's a simple small molecule. The sensitivity is increased, and the SDS is afterwards if you want to blot, ideally for immunoblotting, so no problem to blot it on a membrane as well. Additionally, this necklace structure helps to fix them on the membrane. But don't forget, it is still allergic and skin irritant. So please decide not to use the powder, use the pellets, or even better, a pre-made solution for your health. So what we have now is, after the sample preparation, we know the electric field strength is identical for all the particles, and we have the same charge, everything is minus. We have the same volume and structure, so a linear structure, and so we can separate to the molecular weight. We take now a short trip to the zone electrophoresis. So just presume you have a tank, an anode, a cathode, and a continuous buffer. So there is only one buffer in the system. You might know this quite well from agarose DNA gels. So there is a gel with one buffer inside. That's it. And you have a sample well, and the minus loaded particles or proteins or DNA, does not matter, are evenly distributed in this sample well. So what happens now is when you turn on the electric field, they simply move in the same velocity, and so you see it here, as they were distributed in your sample well, they will show a band. Thus, it is an easy setup, but you will never have a sharp band. You will always have blurry bands. This may be sometimes sufficient, but if you want to see really nearby bands, then this may be a problem and you cannot decide, is this a single band or two bands? So researchers of the world wanted to focus those bands to one line to have a higher resolution later when looking at the separation itself. So before we go deeply into the Lamley buffer system, we have to talk about the isotachophoresis. This is according to Kohlrausch. He was a researcher in 1897, and he tried something. So this on the left side is a glass tube standing upright, and you have a cathode and an anode, and he filled this glass tube with two different buffers. He called it later the leading buffer and the tracing buffer. So the leading buffer is the one below and the tracing buffer above the other one. And they have a specialty. They have a fast electrolyte in the leading buffer and a slow electrolyte in the tracing buffer. And when he turned on the electrical field, he might try to have all the fast electrolytes be at the anode first. But this was not happening, because if this would happen, the fast electrolyte would fastly go to the anode, then you simply have water in the leading buffer, and water is an isolator. So the slow electrolyte would never reach the anode. And he found that the physical reaction there was quite intelligent, if you can say it like that. In between those two liquids, the electrolytes were deprotonized, so you have a minus loaded ion, and this small area then moved, you see it on the right, with the same iso velocity, tachophoresis, from electrophoresis towards the anode, although the mobility of the leading ion is much faster than the tracing ion. So I hope you understood this quite well. Sometimes fancy to think about, but this was then nearly 80 years later, used by a man from the University of Geneva in Switzerland, Dr. Ulrich Lemley. He reported in the Materials and Methods in Nature a new and today very well known tris-glycine electrophoresis system. So we call this tris-glycine buffer system also the Lemley system, or the disk continuous electrophoresis system. Here is a picture of this Nature literature report, and you see maybe what you are doing all of the time in your lab. It is somewhat a buffer below and above, and then you have it seems like a gel with a huge pore size and small pore size. You have some pH here and molarities, and you have here the stacking gel and the resolving or the separating gel. This is what you might use all of the time, but we will go into a deeper look shortly. So this is what we are talking about. It's the classical homogeneous gel. You can also do a gradient, and if you want to know how such gels are made and casted, then I want to invite you to go to our YouTube channel and watch the gel casting webinar again. But we talk about that. So we have a 4% stacking gel and a 12% separation gel. And this is a classical setup. So you have a buffer tank at the anode side and the cathode side that is only connected with the gel. I say this exactly because normally in between those buffer tanks should be no connection. So the only connection for the electrical field is through the gel, not around the gel. Around the gel would be a classical zone electrophoresis gel, like an agarose gel for DNA, a submerged chamber or yeah, a horizontal DNA chamber. But no, we want a complete cut off of both buffer tanks, and they are only connected through the gel matrix. So at the upper buffer tank, we have a running buffer. Here is the recipe for the 10x buffer. So you have tris inside and glycine and SDS. But this glycine is the main particle that is important for the tris-glycine electrophoresis theory or application. Then there is the stacking gel with the stacking gel buffer. It's also tris inside. Tris is unimportant, it's just a buffer, but this is buffered to a pH of 6.8, and the main particle or ion that we take a look at is the chloride. Same goes with the separation gel. So here you have tris inside and also the chlorides, but with a pH of 8.8. This will be important in a second. So how it works. This is a stacking gel. So above here you have the buffer tank, and below here you have the stacking gel, and in between the proteins are loaded. So in the running buffer you have glycine, and when glycine enters the stacking gel, it will have a pH of 6.8. And at 6.8, you see it on the right, glycine is nearly in his neutral or Zwitter-ion state. So it has maximum minus and plus. Just a short sentence to that. Please be careful when casting your stacking gel that the pH is exactly 6.8. The worst thing that could happen is that it is 7.0, then it will not work at all. Or you have a completely other pH, for example, 7.5 or 6 or so, then the complete chemistry is destroyed as well. It must have these 6.8 in pH to work. So please check your pH meter and calibrate it always to be sure that this is 6.8. So in the stacking gel buffer, you have this so-called the chlorides I talked about. So you can imagine chloride is a small, very, very small molecule and is thus a fast electrolyte. So remind the slide I showed you with the isotachophoresis, so a fast electrolyte. And here you have a slow electrolyte because the glycine is nearly not moving. So nearly to the Zwitter ionic state. And so when glycine, the proteins, and the chlorides entering this stacking gel with pH 6.8, you will have this isotachophoresis effect, where the chloride is the leading ion, the glycine is the tracing ion, and the proteins are caught in between. And this is the effect in your stacking gel when you see that you have a razor sharp running border moving slowly towards the separation gel. It should be like that. If you do not have a razor sharp band, then there is something wrong. Just to mention, you don't want to have a sieving effect. Thus, the polyacrylamide matrix will be around 4%. You casted that before, because a sieving effect would also destroy this isotachophoresis and this sharpening of the bands in your stacking gel. At the end of the stacking gel, you will have the separation gel. And now this package of glycine, proteins, and chlorides will pass a pH border. So it switches to the pH of 8.8, and now you see the glycine is loaded and not neutral or zwitterionic. So it is now a fast electrolyte. So the proteins that are stacked will enter, the glycine will switch to a fast electrolyte and will run as fast as the fast electrolyte chloride of the separation gel buffer in front of the proteins. They will be quite fast at the anode, I can promise, so about 5 to 10 minutes. Then there is no glycine, no chloride left in the system, and now the proteins are sieved with a, for example, 12% polyacrylamide gel, are now sieved, and the proteins are separated according to their molecular weight. We come to the troubleshoot. The most often explained issue that we have at Serva is a long run. So, well, I started my electrophoresis, and after 1 hour, my proteins are still at the half of the gel, something like that. Or the blurry bands, my bands do not get sharp. So, when you think back to the slides before, there can be different things that could happen. So first of all, there can be a leakage. So the electrical field should only pass through the gel. If it is not passing the gel, then the two buffers are combined, let's say, and the complete setting of this isotachophoresis is destroyed. So check for leakage first. Then it could be the pH. The pH meter can be imprecise. I explained that just a slide before. So, and what nobody knows, I guess, you can also watch the gel casting webinar, because I have made some tips here for preparing gels in advance. Some cast their gels with the separating and stacking gel and put them in the fridge. Of course, when you have the one pH in one gel and the other pH in the other gel, then you will have a mix of the pH between the gels if you store them long. So I prefer to prepare the separating gel only and store it in the fridge, and the stacking gel should always be casted freshly half an hour, 1 hour before you use the gel. And the third possibility why it comes to those blurry bands is the chlorides are in the running buffer. Because if you feed the complete system over and over and over again with chlorides, you will not have a discontinuous buffer system. You have one buffer system, and this is zone electrophoresis. And I showed the slide where you see that you never can get a sharpening of the bands because it's zone electrophoresis. So why do one should get chlorides in the buffer? Well, often the tris is stored next to the tris HCl. And you can, by chance, grab the flask of tris HCl. So avoid this. Only use the tris base. Yeah? And I must admit that when I watch at the Serva chemical storage, they were indeed standing side by side, the tris and the tris hydrochloride. So it was yesterday. I made the picture yesterday with my phone. So yes, it's true. We also store them next to each other and take a last look before you measure it. Is it really the tris base or is it the tris HCl? There was a question in the last webinar, and I just want to put this in as well. If you can use other acids to make the pH. No, you can't, because now you know that as watcher of this webinar, it's the chloride that is needed as a fast electrolyte for the isotachophoresis. So if you use other acids, they may be bigger in size or something else, have a weaker pK or something like that, and you will destroy your isotachophoresis. The same goes with buffering back. So as you work with 37% HCl to adjust the pH, it might be that the second drop is too much and you are over the given pH. So don't buffer it back. Yeah, just throw it away and make it new and be more careful for the next setup. So this was it from my side. Now you know all the basics and all the important stuff for your SDS page, and I hope that this might help when you have problems to troubleshoot and to know where you can take a look at and how to get rid of it. Just short advertisement. Our next webinar is at the 12th of June, 1400 again. It's fast blotting mini gels in 15 minutes. And we are also just recently discussing if to do a summer break and start then in August, September, or if we go on every month. So please take a look on our website where you find all the dates for the comings. So thank you for your attention, and I'm open for your questions. Let's see if we have some.